Good morning everyone. Welcome to the 8th lecture of VLSI Interconnects course. Today we will be looking into how to simulate RC interconnects on SPICE. So far what we have seen is a distributed model for RC interconnects. We have seen the Elmore delay in interconnects. We have seen Elmore delay in branch interconnects, and we have seen pi equivalent model, which helps us emulate the interconnect delay as per the Elmore expression. So with that background, we will today do some simulations and test some of the theoretical expressions which we had derived in the previous lectures. So what we will do is that we will compare a lumped RC model and a distributed model for interconnect. We will look into pi equivalent models and verify whether pi equivalent models give us more accurate results. And then we will, using these pi equivalent models, we will simulate branched interconnect. So for this simulation, if you go to the Moodle page, I have created a tab for simulations. Here I have given some links to software which can be used for simulator. I will be using LT Spice simulator. If you are familiar with any other SPICE or any other circuit simulator and you have access to it, you are welcome to use that software as well. There is no restriction on the software to use to be used for this. We just have to create some RC circuits and simulate those. So any software that works is good. If you are not familiar with any software, if you, for example, if you don't have access to ADS or Cadence or other SPICE simulators, I would recommend a simple and easy to use simulator, which is LT Spice. I have given the link here. If you go to the link, this is I think provided by Analog Devices. It's free. So for Windows as well as Mac, download file is available. If you are using Linux, as I am using, you will have to use a Windows version and use Wine to install the simulator on Linux. So I am using Linux, so I have been successfully I have been able to successfully install this simulator on Linux as well. That should not be an issue. If you, for some reason, if you don't want to install a software, you can also use any online simulator. One of the good and reliable online simulator is Multisim. You can create a account here. Go to sign up, create an account, and then you would be able to construct some basic circuits. We will be requiring basic circuits only. The only catch with using Multisim is that there is a restriction on the number of elements that you can use with the free account. So if you can install LT Spice simulator. Once you have installed the simulator, then you can open this worksheet. So simulation session for RC interconnects. If you open it, you can see I have created a worksheet there. Here I have given you some problems to work on. So based on the theory and your knowledge of SPICE simulator, you should be able to simulate the circuit. So watching this video is not as essential as doing this simulation on your own. If you are familiar with circuit simulators, just go ahead, open this worksheet, go ahead and simulate it and validate all the theoretical claims which we had made. If you are not familiar with that, in that case, you can proceed with this video where I will tell you step by step how to create some basic structures and then how to look at the waveforms and what we can infer from these waveforms. So I have broken the worksheet into several segments here in this notebook. So to start with, I have given you some interconnect parameters. I've given you the length of interconnect, which is 1000 micrometers or 1 mm. I've given the resistance per unit length as 0.02 ohm per micrometer. Capacitance per unit length is 0.5 femtofarad per micrometer. Now what we want to do is we want to simulate an interconnect with these parameters, and we want to find the delay, or maybe say compare the delay with our theoretical claims. So the first part of this requires you to simulate the output signal considering a single lumped RC model. So in the first part, we consider the interconnect to be a simple lumped RC. There is a lumped R and there is a lumped capacitance, and then see what is the simulated RC delay and does this match with the theoretical value. To simulate this, what we essentially want is that we at the input we are giving a signal like this, right? So it can go on till infinity if we are just interested in delay, but we can also create a clock like this, and then at the output what we are interested in is the output waveform. So how your delay will look like for this clock. So this you can go on. So for that purpose, this input voltage we consider it to be a clock of 2 gigahertz. Again, the frequency here is not important. Any frequency that satisfies or that has a time period enough to show us the charging and discharging in the case of off state, that is good enough, right? So we will consider input clock of 2 gigahertz and a peak voltage 1 volts and a duty cycle 50%. So again, even if you take it to be 2.5 gigahertz, it should be I mean your time period will be small. If you take 1 gigahertz, that should also be okay. So your clock frequency for analysis would depend on your interconnect parameters. Depending on your interconnect parameters, you have to select the clock input clock appropriately so that you are able to see the charging and discharging components. Right, so if I am considering a lumped model, all I have is R interconnect and C interconnect. I have been given the values of R, C and L. So my interconnect resistance R will be R into L. So if I do that, what I get is, let me check. So you would have 0.02 multiplied by 1000, or you have 20 ohms. And similarly, your C interconnect would be 0.5 femtofarad multiplied by 1000. So you have 0.5 picofarad. So you have 0.5 picofarad. Now all you have to do is that you have to go ahead and solve for the create the circuit and run the simulation. So what would be the delay here? So R interconnect and to C interconnect, if I want to just write it down, it would be 20 into 0.5 picofarad. So this is equal to how much? 10, sorry, not picofarad, here it will be picosecond. Now your delay is how much? 10 picoseconds, right? So let us see if we break it down into let us create a circuit and see. So for the first case, I am creating a circuit from scratch. So here you just have to define the components and just drag and drop. So here if you want to first create something, so there will be lot of components here. I want a voltage, so I just select a voltage here, voltage source, and then I drop it. Then I want a resistor. I can so there are also these shortcuts here, these you can click here, so resistor, capacitor and all. There are also hotkeys associated with it. Since I am using it for some time, I am now familiar with it. So for example, if I press R, I can get a resistance, and if I press C, I can get a capacitance, and I place it there. If I want a ground, I create a ground, and then I can create a ground here as well. I want to connect these through lines, so then I go here, and this is wire, so I connect it with wire. So, or I can just press F3 and connect it. So let me complete the circuit. Now that I've done the connections, let me give some values here. So if I right click here, I can give the value of resistance. The unit is ohm, so it was 20 ohms. The value here, I mean, so there are two things. One is the label, so I can also change the label. So let me make it R interconnect, and similarly that I can make it C interconnect, and I can set the values also. So the value here is 0.5 pico, and unit here is farad. So create it. For your window, if you are using the default values, your font size and everything will be very small. So for that, you go to the control panel. If you want to change the line widths and other properties of the drawing window, you can just change it from here. So for example, I can change the line width from here. This might not be visible on the recording, so let me make it even more thick. Right, I can also change the font size from here, so I can change it. So once I have done that, so I have defined my resistor and capacitor. Now I want to define the voltage. So if I right click, it asks me to give some DC value, but I don't want to give a DC value. I want to give a clock. So let me show it again. So I go for advance. In advance, I can create exponential sign, other things also, but what I want is a pulse. I want the initial value to be 0. V on, the on state voltage is 1, and delay, let me not include a delay to start with. Rise time, this is of the input pulse, so we want this to be as small as possible. So let me give it, let me give 0.01 picofarad for that. Not picofarad, sorry, picoseconds for that. On time, so on time will depend on your clock frequency. So if your clock frequency is 2 gigahertz, your time period would be 500 nanometers. No, sorry, 0.5 nanometers, or 25 or 500 picoseconds. And if so basically your on time can be half of that. So I'm taking it as 250 picoseconds, and my time period as 500 picoseconds, and number of cycles let me take to be. So now I defined my input voltage. When I run it for the first time, it will also ask me like the stop time, for how long should this simulator run. So here I just want it to run for 500 picoseconds. So this is what comes. So yeah, I have simulated it, and so the simulation, once I simulated, some raw things comes here. The time axis goes till 500. Now I have to select the voltages. Before I do that, let me create some labels also, so for easy tracking. So let me create a V in, and okay, let me V in, and let me place it here, and then let me create another label. So this is V out, and let me place it here. Right now, if I just want to see the input, so this is my input, starts at 0, goes up, then remains 1 till 250 picoseconds, then becomes 0. Right? If I want to look at my output voltage, it is something like this. Right? Now I also want to find delay. So what I find easier many times is to include a offset in my input signal itself. So if I create an offset in my input signal and then I run, so my on starts from here, so it's easier for me to track the delay. So let me zoom into this part and look at the delay. So for looking at the delay, let me click V out. So I'm not sure whether these values will come up in screen capture, but I will just say the values verbally as well. So if I just drag this cursor to 0.63 or 600 millivolts, the closest to that, I can see that my horizontal line, so I mean this point is 20 picoseconds and my starting time is 10 picoseconds, so my delay comes out to be 10 picoseconds. So with this I can actually validate that okay, if I have a learned circuit, this is my circuit is working, my simulator is working well. I have been able to create the clock frequency of some appropriate value, and I should be able to see and analyze the delays for distributed interconnect model as well. So with this we can say that okay, I mean our basic circuit simulator is working well. Now let us go to the distributed model. For this, what we have to do is that we have to divide this in 5 sections. So what we will do is that you have an interconnect. Now instead of one single element, you have 5 elements: R1, R2, R3, R4, R5, and all of them are equal. So I have given the name R1 here in my worksheet. So what is R1? R1 is the resistance per unit length into delta X. And what is delta X? Delta X is the entire length of the interconnect by the number of segments. So in this case there are 5 segments, so my L by so my delta X will be 1 mm by 5. If I substitute the value of delta X here, what I get is R1 is equal to RL by N, or in other words, what I have is like RL was 20 ohms, so that divided by 5, or in 5 equal segments, so I have 4 ohms as R1. So all these are 4 ohms, and then capacitances are 0.1 picofarad, because the entire interconnect capacitance was 0.5 picofarad. So I divide it by 5 to get 0.1 picofarad. Right? So similarly, I can segment this into 10 sections as well. Before you proceed, I would recommend that you go to the simulator. It's much easier here. So I would recommend that you take this, or say, I think, yeah, there is a option to copy it. Oh, sorry, let me close this part. You take this, change the value here. So from 20 ohm you change the value to 4 ohms, and capacitance you change from 0.5 to 0.1, and then what you can do is that you have to copy it. So create this, create this part, create a copy, then again create a copy, and yeah, let me pen through. Create a copy 4 and then 5, and then you connect all of these. Let's zoom in, want to get rid of these intermediate nodes, so or you want to change the value here. So this is final v out, so let me just name it final v out, of say 5 stages, and then again you can simulate it, run the simulation and check the this is v in and then this is your v out. So again you can zoom in and check the simulation and see what is your delay. You can then break this into 10 segments. Once you break it into 10 segments, the resistance of one segment would be 2 ohms, or say each segment would be 2 ohms, and capacitance of each segment would be 0.05 picofarad. You should go ahead and create that on your own. And then what would be the theoretical value of Elmore delay? So if you check that, what you would have is RCL square by 2. So if you solve this, you would get the Elmore delay to be 5 picoseconds, which is half that of the lumped model. So what you want to then validate is simulate this for 5 stages and then 10 stages and also for lumped element, and then see with increasing the number of elements is your delay converging to that of the Elmore delay. So I think I've already solved that problem, and I have a file, so let me open it so it will save time. So I've already solved it. You can either create multiple files, or if you want to compare, what you can also do is that you can have it all together. So okay, let me rename this segment is V out 5, and let me name this segment as V out 10. Right, so this is the entire circuit. So this part here, I have taken the same single source. This part here is a lumped model. This part here is an interconnect, RC interconnect with 5 segments. Here it's with 10 segments. Now let me run the simulation, and now let me check the voltage. So this is my input voltage. This is the output voltage for lumped model. This is the output voltage for 5 segments of interconnect. This is that for the 10 segments. So we can see that from going from 5 segments to 10 segments, the delay is actually decreasing, and it seems to be converging somewhere. So let us zoom in and look at where is it converging. So if I zoom in here, this starts from 10 picoseconds. So I can just have yeah, this is my lumped model. So for the lumped model, if I go and take 0.63, so my delay is 20. So the value here is 20 picoseconds. Input starts at 10 picoseconds, so my delay is 10 picoseconds here. If I look at this for 5 stages at 0.63, my delay, I don't know whether the value will be captured here in the recording, but here it is showing 16 picoseconds. You can check it for yourself. So this is close to 5 picoseconds. This seems to be converging to 5 picoseconds, but it's not yet there. There is still an error of 1 picosecond there. Now if I look at V out for 10 segments, in that case my 6.3, let me make it 6.3, yeah. So here now my delay would come out to be 5.57 picoseconds. My delay comes out to be 5.57 picoseconds. This is for 10 stages. So we can see that as the number of segments is increasing, my delay is finally converging to the theoretical value of 5 picoseconds. You can also test it for 20 segments and see whether your delay converges or say comes closer to your Elmore delay of 5 picoseconds or not. Right, so okay, yeah, right. So here now what we will do is that we will in the next part you have to simulate the interconnect with pi equivalent and pi 2 equivalent models. So you can see that, I mean, if you have 5 segments, which is also like 20 elements, then you can get a reasonably accurate delay. If you take 10 segments, which gives you 20 components, in that case you come more closer to your Elmore delay. But what if you don't want to have that many number of elements? So that was one of the reasons why we had looked into the pi equivalent model. So in pi equivalent model, we break down the interconnect in this lumped model, this model which looks like pi. The value here is RL and the value of capacitance is CL by 2. Similarly, if I have a pi 2 model, in that case I also break the resistance RL by 2. So I get 10 ohms and 10 ohms for these two segments, and here I would have this divided by 4, so it would become 0.125 picofarads, this would become 0.25 picofarads, this would also become 0.125 picofarads. Right, so what you should now do is that you should simulate the pi equivalent model and pi 2 equivalent model and then see whether pi and pi equivalent model gives you a more accurate estimate of your output response with lesser number of elements. So you need to validate it on your own. I will go ahead and show you an already created structure. Yes. So what I have here is a pi 1 equivalent model, a pi 2 equivalent model, and a distributed model. So here I have a distributed model with 10 segments. So let me include some text here to identify that. So this here is a distributed model, the top one. Now let us simulate it and see the. So this is for the pi equivalent model. You can also have a lumped RC model that I have not included, which is very crude. And this is for pi 2 equivalent model, and this is for a distributed model with 20 elements. So how many number of elements are there in pi 2 equivalent model? 1, 2, 3, 4, 5. How many number of elements are there in this distributed model with 10 segments? 20. So for a single wire you would require 20 segments, but you could replace it possibly by 5 elements here, or if you are okay with the accuracy, even with 3 elements like this. Let us zoom into this region and see how accurately this pi model is modeling. So okay, let me zoom in further. Right, so I can see my pi 2 equivalent model. If I look at this, this is around 15.128, and my distributed, so this has converged to a lot more closer to the Elmore model, Elmore delay. So Elmore delay was 5 picoseconds. With this pi 2 equivalent model, I am almost getting 5.1 picoseconds, and actually it should be lower because I am looking at value of 3.631 millivolts. If I look at the distributed model, then I should be getting somewhere around 5.5, as we had seen in the previous. Yeah, so I'm getting something somewhere around 5.58 picoseconds with 10 elements. So we can already see that this pi model is giving us the required accuracy in delay with less number of elements. Right now, once we have validated the pi equivalent model, we will now extend this for a branched interconnect and interconnect model as well. Before we do that, after looking at this discussion, you may be tempted to equate the Elmore delay with the 60% delay, but I must emphasize that Elmore delay does not by definition mean 63% delay. It is only for RC ladder circuits that it turns out to be close to 63. So in all the analysis up till this point, what I was doing, how was I testing the delay? I was looking at the 63% delay for that RC network, and where was the output voltage becoming 0.63 times the final output voltage, and that was converging with or coinciding with my Elmore delay. But you should not forget that Elmore delay does not by definition mean 63% delay. It's only in this RC ladder circuits that it turns out to be the same. So for example, if I had a linear output voltage like this, so if my V out was something like this, then my V out prime is the derivative of V out of t would be something like this, right? And here if I now check the centroid of this would come out to be, so this would come out to be 0.5. so this would be my delay. This is my delay. So it depends on the shape of this waveform. So by definition, Elmore delay, I am again re-emphasizing, Elmore delay does not by definition mean 63% delay. For example, if my output was linearly varying, I would get my delay to be around 50%. Elmore delay would be my 50% delay for a linearly charging of capacitor. right? So please do not confuse Elmore delay with 63% delay, even though we have used the check on Elmore delay using the criteria that my output voltage becomes 63% of the final value. Right, now let us extend this for a interconnect tree. We have seen an example like this in the lecture earlier, and we had also seen the equivalent model for this, and we had seen how to get the values of capacitances for these all these components. So here I have written down the values of R1, RL1, RL2, CL1, CL2. The values of L1 and L2 are given. L1 and L2 are given. So you should now go ahead and compute the delay. So just a point to note that you may have to decrease the clock frequency of the source in this part. Why? Because you have a longer circuit and your delay is more. So it may happen that if your on time is just 200 picoseconds or 250 picoseconds, it might not be enough to completely charge the interconnect to the final value. So you may have to decrease the clock frequency or increase the time period, right? So I think I have also already made that circuit, so let me just show you the final results. What you should do is you should go ahead and test it on your own. So this is a circuit which is already created. There is this, okay, let me, so this is the input, this is the pi equivalent, the value you can compute here. So value of this capacitance is this CL1 by 2 plus CL2, that should be here, and similarly you can fill in the other values of resistors and capacitors as well. For this circuit you can also compute the Elmore delay, right? So TD2 and TD5, you can compute the delay between say 0.1 and 2 and 1 and 5, or say 0 and 2. I have used 0, so 0 and 2 and 0 and 5, and then you can compare it with what would mean for the from the simulator. So now let us see what is the output voltage. So this is my voltage 1, then I have a voltage 2, and then I have voltage V out 5. So red curve is the output, red curve is the output voltage at node 5. So if I zoom in here, and if I let me check the Elmore delay for this one. So again I'm just checking for the delay from here, right? So let me take it to 0.63. .29, yeah, 0.63. So what I'm getting is 140 picoseconds value here. Again, it starts from 10 picoseconds. So my delay is 130 picoseconds. If I check the value for Elmore delay for TD5, it comes out to be 130 picoseconds. So far it looks good that even for this distributed RC model with branching and all, I am getting my delay to be close to 130 picoseconds. But what if I look at the delay for this voltage node here? So if I just look at the delay here, so let me again bring it to 0.63. Yeah, so now I am getting my delay to be 110, 63% delay to be 111 picoseconds. And no, not the delay, this is this value. If I subtract 10 out of it, so I am getting somewhere around 100, and the 63% delay would be 101 picosecond or something. 101 picoseconds, yes, 101 picoseconds, 101.5 picoseconds. But if I look at the Elmore delay, what I get is 105 picoseconds. Why is this discrepancy now? Because as we had said that Elmore delay by definition does not guarantee a 63% delay. It's only for an RC charging circuit that it comes out to be close to the a simple RC charging circuit, it comes out to be close to 63% delay. If when I'm looking at the voltage on the node 5 or the output voltage at node 5, I am traveling more like a distributed model, and then this branching is not that significant. But when I am going from here to here, all this capacitance is charging is being loaded to this point, right? So in that case, this deviation is more with the that of RC delay. So even you can see it from the waveform, right? Even from this waveform, this does not look to be like a simple RC charging. So that's why there is a deviation in the coincidence of Elmore delay and the 63% delay. So this is the subtle variation that should be kept in mind. With it, I will stop this lecture here. For your assignment, I have loaded another, I have given another problem. So you have to repeat exercise 1 and exercise 2 by considering a source resistance RD of 20 ohm and a load capacitance of 500 picofarad. So here in all these circuits, you have to create another resistor RD and a load capacitance CL in all these nodes. And even when you are simulating it for a single interconnect, you have to consider a load capacitance here and driver resistance here, and then again repeat the entire exercise. Again, you may have to further reduce the clock frequency to look at the waveforms properly. So your on time should be enough that your capacitor is, all capacitors are being charged. You may have to adjust that. With it, I will stop this lecture here, and from the next lecture onwards, we will start with module 2 of the course, which is on the RLC, resistor inductor capacitor modeling of interconnects. Till then, good day. See you in the next lecture.